Okay.
Please switch on to the full screen.
Yeah, it's full screen. It's showing.
Go to the slideshow mode.
Is it visible?
No, you have to switch to slideshow mode.
It's into the slideshow only.
I can't see that. I'm seeing
Just
the old screen
It's
where.
I think there is some technical glitch. Wait a second.
no problem. Let me. Is it visible
Yeah.
now? Yeah, Mr. Bollini.
Yeah.
Yeah. Okay. Great.
Yeah.
Thank you.
Okay. Yeah. Yeah. Okay. So hello everyone. My name is Rahul Bollini. I'm going to talk about electric vehicles, and then I'll get into batteries and further again about uh, battery management system (BMS). Yeah. So next, can we go next? Next. Yeah. So what is an electric vehicle? Electric vehicles are vehicles that are powered by electrical energy. So why is it gaining so much traction? Firstly, it has an environmental benefit, and secondly, they have running costs, and thirdly, the manufacturing. Okay, the batteries are expensive, yes, but if you see on an overall, they have lesser parts. So anywhere, basic ICE internal combustion engine vehicles have up to 2,000 parts. EVs have as low as 20 parts, and EVs are more efficient. Um, ICE operates anywhere, if you take a diesel generator or a diesel car, they operate anywhere between 16 to 18% efficiency when the fuel is burning. But on the other hand, if you see battery operated vehicles, they operate 90 plus. They have an efficiency of 90 plus percentage. Yeah. So you can go to the next slide. Let's talk a little bit about the history of electric vehicles. So it all started in 1827 when a priest from Hungary, just out of nowhere, thought, okay, he just put an electric motor with stator, rotor, and commutator to a small car, to a tiny car. And so that is the practical, the first ever invention of electric vehicle. And then the US had a good trend of EVs, especially in the early 1900s and the late 1800s. There were a lot of EVs selling, and back in the day, they didn't have any range anxiety because the roads were not so big, and there were not so many highways and all that. So it was mostly local commuting and all that. But all this changed in 1908 when Ford launched the Model T. So in 1908, they launched a vehicle, petrol-based vehicle, costing less than half, and that's when there was a downfall in the electric vehicles market. And then petrol vehicle, and simultaneously, parallelly, there were developments in the highways and all that, and electric vehicles never had a chance. So again, US tried to restart the US Energy Protection Agency in late 1900s. They tried to push again for EVs, and that's when General Motors also tried to make some models and all that. But it was planned in a way that they don't work out so well because there are 2,000 parts in an ICE vehicle, and they make a lot of money. These automobile companies make a lot of money in spare parts and servicing and all that. And we can see that vehicle in the next slide. Yeah, can you go next? Yeah. On the right, you can see a red car. The way it is designed, it is designed in a way so that people don't get attracted to it. Purposely, it was designed that way, and it was not sold; it was leased. So General Motors had a complete control over the vehicle, and after a few years, they removed the vehicles from the road and made sure that petrol vehicles kept selling and EVs didn't do it. So, and on the left, you can see a charging station. This is the early 1900s and all that. Obviously, they were using lead acid batteries back in the day. The way it was being charged, it was not at all sophisticated like today how we have DC fast charging. Yeah, can we go next? So let's talk about the types of electric vehicles. So I saw someone asking a question: hybrid vehicles will take over the market, or EVs will take over? So, like the earlier speaker said, rightly said, hybrid vehicles is more of a transition where you have both, uh, preferably petrol and then battery operated. But problem with hybrid vehicles is the making cost is very high because you need to have two systems, one engine and one motor, and the cost just shoots up. So, for example, you can take a Toyota Camry hybrid. It sells for about 35 to 40 lakhs. So, that is not really the market segment that India has. India has the market segment where anywhere people are looking to buy a car between 8 to 12 lakhs. That is the market segment where if you see Maruti sells the highest number of cars and followed by Hyundai. So hybrid electric vehicles, it's not possible to make such vehicles in that budget. So that never really took off, and even government knew that, so that's why they never really encouraged. They were like, okay, let's go bypass and just go all in with electric vehicles, complete electric vehicles. So let's talk a little bit about hybrid electric vehicles. So hybrid electric vehicles is basically a hybrid system where uh, it switches to battery mode whenever the vehicle is driving slow. The driver doesn't have any control over it. But when you compare it with a plug-in hybrid, the driver has a control. There will be a switch where you can switch off the petrol mode or you can switch off the EV mode and you can charge the battery. But if you see a hybrid electric vehicle, it's completely charged directly by the dynamo which is supposed to charge the lead acid battery. That would be charging here as well. And obviously there'll be regenerative braking system as well, and which will be charging the batteries. But the driver doesn't have any kind of option when to switch and all. So it is basically, it works as it improves the mileage of the vehicle. That's the whole point of a HEV. But when you come to PHEV, the whole idea of developing a PHEV was that people can drive electric or at all times, and whenever they are about to run out of charge, they can just go fill some petrol and keep using the vehicle until they come back to a charging station or until they can come back home and charge overnight. So that's yeah. So if you see the HEVs, Toyota Prius was there, which never really took off in India. It was too expensive. Toyota Camry again was expensive, and Ford Focus and Ford Fusion never came to India. It's the American model. But coming to plug-in again, Prius plug-in never took off. Fiat 500e was more of a UK model, and if you see, someone saying hydrogen powered vehicle technology is also good. That's not a real technology. That is all in development mode actually. Only there is one Toyota Mirai. There is only one vehicle which is being tested in the state of California, US. Other than that, there's nobody actually commercially promoting. So I like to talk about technologies which are existing rather than upcoming. I see thousands of papers, thousands of articles. People talk about this is coming, that is coming, but we have seen history will tell you that not everything is here to stay. Not everything is going to come so fast and so easily. Basically, in technology, there's something called technology readiness level. So TRL, by the time it reaches 9, only then it is commercialized. So most of the people, the labs and the companies, the startups, they start advertising when they are at 3. They are at the basics of prototype building. Even when it's not proven, they start publishing papers and all. It's good for reference in the scientific field and all that, but the mass market doesn't work like that. You need to have proven track record. The vehicle has to be tested on field, and you need to provide the warranty backed up with data. So it's not that easy. So obviously hydrogen will come, but yeah, it'll take its own time. So let's move to the next one. So here we'll be talking about battery electric vehicle and hydrogen. So battery electric vehicle is what we see these days, all this two-wheeler, which is a very hot market, and then Tata Nexon is a very good market. So it has no petrol engine and petrol tank and anything. It will be a pure electric vehicle, and it has good efficiency. But if you are looking for a vehicle with high range, obviously it will have more batteries, and it will drive the price up. So this is one barrier, why electric vehicle adoption is at the slow rate. And the other barrier would be the range anxiety, that what if I run out of charge? What do I do? Where do I go? Who will rescue me? That is always there. So these are the two reasons why EV adoption is slower, especially in cars. But two-wheeler is always, it's a very hot market right now. In fact, there was a more than 300% increase, growth, year-on-year growth when you compare 2021 with 2020. Yeah, and then fuel cell electric is basically, the hydrogen vehicle which someone was just talking about. So there, the motor will be similar. It will be electric kind of motor, but there'll be a place where a reaction happens and hydrogen gives out an electron, and then that electron goes to the motor. It is basically electric motor only. So only the instead of battery, you have a tank where you store hydrogen, and then there'll be a reaction happening place where after where from where the fuel is given out, and then from there the electron goes all the way to the motor. So dynamics is kind of halfway similar to battery electric vehicle. The advantage of hydrogen, why people are talking about it all the time, is you can just refill your car within minutes. And batteries, you can't do that. It takes you at least the fastest charging batteries that you see generally commercially available is say 80% in 30 minutes, something like that. So 30 minutes is a lot of time considering if charging stations are full and there's a waiting line and three people are actually standing in front of you. So that's a waiting time of about 2 hours. So that's technically, practically it's a challenge. That's why everybody's trying to move towards hydrogen. But hydrogen has its own challenges. It's practically a hydrogen bomb if there are leakages and all that. So there are safety aspects being worked on. Yes. Let's go to the next one. So this is the basic build, how it is done. Hybrid electric vehicle has both gasoline engine as well as electric motor, and plug-in also has, but you can charge the vehicle. That's why it's called plug-in. And battery electric vehicle doesn't have a petrol or diesel engine. It will be a pure battery based. Yeah. Let's go next. Let's talk about types of batteries. So these are the top. These are the most type of batteries that you will be coming across, generally speaking. So let's talk about lithium-ion battery, which is the hot topic these days. Everybody's all the EVs use this technology. So it's the most common type of battery used in electric cars or all the electric vehicles to be frank. And and most portable electronics. If you see your cell phone and if you see your laptop, they all use lithium-ion batteries. So the advantage is they are very compact and the power density is very high. So for a very small battery, you can expect a very good amount of power. It can store good amount of energy, and it can operate at higher temperatures. And the self-discharge rate, which is a big challenge in lead-acid batteries. Suppose when you have a car and you're not using it for a few months, and then suppose you go out of station or something and you come back, and then you see the battery is dead. Yeah. So that's not a case which happens in lithium-ion batteries. So because the self-discharge rate is less than 5%. So even after a few months when you come back, the battery is still intact. And there are a lot of recycling things which are being, practiced these days in lithium-ion batteries. So a few years ago that was missing. Now companies are taking it seriously. In fact, 2 days back, LG signed agreement with LI Cycle. And so recycling is also taken very, very seriously. The advantage of lead acid battery has always been that it has a recyclability of above 90%. Now lithium-ion battery is also joining in the race. And let's talk a little bit about lead acid battery. It's the cheapest type of batteries available. So even today, if you see a lot of e-rickshaws, they use lead acid batteries for price reasons. And it also gives you a good kind of power and all that. Only thing is they don't have good life, and you cannot use the complete energy out of it. They cannot give you the complete energy, and it is a challenge, especially it doesn't perform very well in the winter. So these kind of issues are always there. So these days, the advanced lead acid batteries are being made in two variants. One is where the batteries will be lighter with same performance, and the other one is the batteries will perform as equal to lithium-ion batteries, but they'll be heavier. So you cannot expect both of them happening in the same lead acid battery, lighter and perform very good. So two type of aspects are being developed. So the heavier one with good performance as good as the lithium-ion batteries are being made and tested and all that. So it will be used in stationary places, commercial spaces where the battery weight or the volume doesn't really matter. Let's talk a little bit about nickel metal hydride. So this is the one which was used earlier in the hybrid electric vehicles when it first came out. So if you probably saw a Toyota Prius hybrid vehicle, that used to use this one. So this has a very good cycle life. Life is very good, but it has its own issue. The self discharge rate is very high, so like similar to lead acid battery, and nickel is highly poisonous. It is a very poisonous thing. Even while recycling, there will be a lot of discharges and all that happening, and that was the main environmental concern for across the world, and they tried to get rid of the nickel technology altogether, the nickel cadmium and nickel metal hydride and all that. And for those reasons, it was phased out, and lithium-ion batteries took over nickel metal hydride. So once you see plug-in hybrid vehicles, and then it was all lithium-ion batteries. And let's talk about ultra capacitors or super capacitors. This is also a very hot topic where people are talking about. Tesla acquired Maxwell company, and they are a super capacitors company. So advantages of super capacitors over lithium-ion batteries is they have a very high cycle life, like it much higher. You can easily say about 50 times higher cycle life, and they can charge very fast. But it comes with a challenge. They are super bulky, and they are very heavy. And the next next thing is the voltage. The voltage is not very constant. The delivering voltage, so it becomes a very difficult. Yeah, it becomes a big challenge to develop a BMS which can uh, work with such fluctuating voltage. So that's why supercapacitor is still under development. It is, and there are some companies using supercapacitors and making it a hybrid with lithium-ion batteries, where you can do a quick charge, little bit of supercapacitors for little bit of traveling distance, and then lithium-ion batteries will take over, something like that. Yeah. So we can go next. Let's talk about lithium-ion batteries. So we'll go deeper in lithium-ion batteries right now. Lithium-ion battery is a secondary battery. Secondary battery is nothing but a rechargeable battery, where lithium ions move from cathode to anode through an electrolyte medium during charge, and during discharge they move from anode to cathode. So lithium-ion batteries, they have a compound as a positive electrode and negative electrode. So generally, whenever you talk, you might be hearing a lot of chemistries, LFP chemistry, NMC chemistry, lithium-ion batteries, and also whenever they talk about chemistries, it's generally the cathode that they're talking about. And anode is pretty much standard. It is a graphite at the negative electrode. So the advantage of lithium-ion batteries is they have high energy density, no memory effect, and low self-discharge. So this is the basics of lithium-ion battery. So we'll go next slide and we'll talk in the. So you might have heard about, like I said, you might have heard about NMC or NCM and LFP, but there are many more chemistries. Like I was saying earlier, when someone was talking about hydrogen, there are many things in the market, but not everything works out. They all have their own drawbacks, and that is the reason why only two technologies come out in the market, and they are adopted, and they last for a very long time. So let's talk about LCO. LCO was a chemistry which was invented in 1991 and commercialized by Sony. And then even today we use it in our cell phones. So any cell phone uses only LCO battery. So advantage of LCO is they give you higher voltage. It gives you the highest voltage, in fact, 3.85 volts. Other batteries max out at 3.6, 3.7. So for higher voltage regions, we use this batteries. And the capacity is also energy density. Overall energy density is good, but LCO is not very safe. So that's the reason why it's not being used in electric vehicles. In electric vehicles, you are supposed to take a lot of cells and put them in series and parallel combination. And when too many of LCO cells are working together, there's always a danger issue aspect and all that to be taken care of. That's why it's completely ignored in the electric vehicle. So in electric vehicle, there are various segments. One is two-wheeler, one is three-wheeler, then there is cars, and then there is buses and all the trucks and all that heavy vehicles. So two-wheelers, they have a very limited space, and the customers, it's more of a B2C market where customers want maximum range, but manufacturers have very limited space. So they go with the highest energy density battery available, which is generally the NMC. And then LFP is something which is a better battery than NMC because in terms of safety, they don't catch fire very easily, and they last long. They have a higher cycle life, and it's cheaper. But they are bulkier and they occupy a lot. They are heavier and they occupy more space. They're bulkier basically. So for those reasons, it's not used in two-wheelers, and it is used in three-wheelers where it goes below the driver's seat or passenger seat, where there's a lot of space and the weight doesn't really matter for a three-wheeler. So, and again, buses it goes, and cars again, there's always a challenge where people, the buyers want maximum range, and cars, the chassis, they have very limited space. So for those reasons, worldwide NMC is used, most of the people. But yes, some people use LFP. If you see Tata Nexon, they use LFP. But if you see Hyundai Kona, MG, EZ, what is that, ZSEV, they all use NMC. And then the other technologies are NCA, which is used by Tesla today, which is lithium, nickel, cobalt, aluminum oxide. And this has the highest energy density, in fact, more than NMC, but it is not so safe to operate in higher temperatures like in India. That's why it never really came to India, and nobody has really experimented in India other than ISRO. And ISRO is able to use it because they're sending it in space applications, not anything on ground in India. So that's also okay. And LMO is also a chemistry which came in between, and it was not so successful. In fact, if you see Nissan vehicles back in the day, Nissan Leaf, they used to use LMO, but they had their own challenges, and it was phased out. And then LNO is another technology which was parallelly developed by Saft France, and that also never really took off. And then again, recently, Johnson Matthey tried to make LNO, and they sold the company because it didn't work out. So, like I said before, many things come, but not everything makes it to the market. And then LNMO is a modified version of an NCM where you remove cobalt because cobalt is the most expensive part, and then which is in development. It should be out, may say, in 2022, and last quarter or something like that, or sometime in 2023. And then there is LMFP, which is a modified version of LFP where you are incorporating manganese, and manganese helps in achieving higher voltage. It will be the same LFP, a kind of stability and long cycle life, safety, and all that, but you get a higher voltage. Instead of 3.2, you can achieve 3.9 volts. So that will be the advantage. We can go to the next slide. Yeah. So let's talk a little bit about C rating. So one of the reasons why lithium-ion batteries have overtaken lead acid batteries in electric vehicles is because of the C rating. Lead acid batteries are very slow in charging, so they don't support a higher C rate of charge. And lithium-ion batteries, of course, they have a C rating of as high as 1 C rating continuously, and VC peak rating and all that. So let's try to understand what is C rating. So lithium-ion cells come with various standard charge and standard discharge conditions. It is advisable to use this cell as close as possible to this condition. For example, the most popular cell coming imported in India, if you see any battery packers supplying a battery to a two-wheeler company, they'll be using probably a 2600 mAh NMC cell. And these cells are generally rated 0.2 C or sometimes 0.5 C also, the standard discharge rating. So when they say 0.2 C rating, it actually means that the cell would perform ideally and would have the maximum cycle life and perform in the best manner if it is being operated at 0.2 C rate, which is 0.2 into 2600 mAh. So that would be 520 milliamps of the power. And one must also understand that discharging at higher rates can deliver lower energy. So if you're discharging a 0.2 C rated cell, say at 0.5 C or 1 C, so you will see that the results will not be matching. So you might be sometimes surprised that why is this 2600 mAh delivering less energy? Why is it discharging at a lower capacity? So the reason is 0.2 C will obviously give more energy when you're discharging. 0.2 C is basically discharging the battery in 5 hours, and 0.5 C is when you're discharging the battery in 2 hours. So when you're discharging the battery in 2 hours, you will get lesser energy. Like a general reference that I tell people is a 0.2 C cell when discharged at 0.5 C is anywhere 95 to 97%, and the same cell when discharged at 1 C is anywhere between 90 to 92%. So this is general, but again, it depends. You can always refer to a data sheet. This is just a caution. I'm just telling you people, when you're actually dealing with batteries, that this is how data is analyzed. So you'll have to understand the C rating and then understand the capacity of the cell itself is changing. Suppose you're putting 10 cells in parallel and selling it to a customer saying it's a 26 AH, but the customer is using it at 1 C. So technically it's not 26 AH. It's, at 1 C rating, it would be 90% capacity. So 26 AH automatically becomes 23.4 AH. So you need to understand that because there's a lot of confusion in the market. I keep getting calls on a daily basis. I'm using this cell, but the range is not coming and all that. So I tell them, see, you need to understand the basics. So that's why I put all this on the paper. I'm sure you'll be getting this slide after the session as well, and we can always refer to it. Yeah. So I put in as much as possible, the technical terms. So it'll be a helpful reference for you people. Yeah. So let's go to the next slide. Yeah. So again, when you're designing a battery pack, so when you connect cells in series, you are, basically trying to achieve the voltage that you want. So it is advisable, it is always recommended to size the battery voltage higher than the voltage required. So suppose, you are using a 48-volt motor. So I've seen in the industry generally, most of the time people use NMC cells, especially coming from China. They say, okay, it's a 3.7 volt, and I will let's talk about 60 volts. So 60 volts, people use 16 cells in series, and 3.7 into 16 is 59.2 volts. And the battery is put in for a 60-volt motor. So if you follow basic physics, you're going against the law of physics. You're supposed to size the battery equal to the motor. Obviously, I'm talking about the nominal voltage, not the full charge voltage, equal to the motor or higher. But I'm seeing the industry, commonly practicing 16S. They're like, I ask them sometimes, they're like, see, it's almost equal. I tell them, no, it's not almost equal. You are from the nominal should be always above or at least equal. So I tell people you have to migrate from 16S to 17S, and the common thing misunderstanding in the market is that 3.7 volt. It's actually not 3.7. If you buy a LG cell, it would tell you 3.6 volt. So actually speaking, the voltage of the cell, if you take the nominal voltage of NMC, is between 3.63 to 3.66 or 3.67. So the Chinese round it off as 3.7. But if you see Panasonic, LG, Samsung, they'll round it off to 3.6. So technically, it is good to round it off as 3.6. And when you see that people are taking 13 cells in series and counting it as 3.7 and all, then they're like, okay, it's coming 48.1 volt, which is a good thing. Then I tell them it's not. No, it's not like that. You need to take the actual cell voltage, which is between 3.63. say or 3.65 and multiplied with 13, then you see the voltage is actually below 48 volts. And then again with aging, these batteries, the nominal voltage tends to shift a little bit down, and then so for various reasons, I tell people you need to oversize the voltage at least by one cell, and that is something. And if your battery is sized at a lower voltage, so it will be drawing more current, and more current means more discharge, a more C rating for the battery. And the C rating of the battery should be kept always kept on the lower side to achieve the first reason is you get more energy at lower C rating, and second thing is the temperatures don't rise. When you're operating at a lower C rating, the temperatures of the battery pack is lower, and whenever there is a heat generation in the battery pack, that's nothing but the energy that's coming from the it's energy from the battery. It's not an external heat generation. So if you are keeping the battery on the cooler side, this energy could have gone to the application and given you higher range. So these are some, back-end reasons why I tell people just add a cell. I know it's going to cost you more, but it's going to give you a lot of benefits. Yeah. So some common recommendations for configuring NMC battery pack. So like I was saying, use 14S instead of 13S for 48 volt application. Use 17S instead of 16S for 60 volt application. Yeah. Let's go to the next slide. Yeah. Let's talk a little bit about lithium-ion battery pack process. The cell is not being manufactured. I have made a lot of cells back in the past, but it's an industry not really taking off. I would say maybe now the PLI scheme has come, say, sometime in 2023, we can expect some good players, big players and big production. But I don't expect anything to happen, to be frank, in the next year, because the setup process itself takes 15 months. So let's talk quickly about lithium-ion battery pack process. Yeah, you take the cells and you put them on a charger discharger, and then you basically put the cells and then charge it full and then discharge it completely to zero. So from 100 to 0, when you discharge it, you will get the capacity of the cell, and based on the capacity, you will be grouping the cells. And then again, those groups are again sent forward for the cell sorting. So this is a cell sorting machine with 11 channel, where you will set up a preset combination of impedance, which is internal resistance, and then OCV, which is the open circuit voltage of the cell. So based on the combinations, you'll be getting outputs of the cell, and those cells will be again the cells coming from the single channel would be used for the same pack. So you'll not be mixing the cells, because this will be the ideal way of packing the cells. You'll be using the most uniform cells in a given pack, and that is the right thing. And then next, you send it for the spot welding, and you put the cells in a cell holder, and then you put a nickel tab, and then you spot weld it basically. Yeah, and then let's go to next. And then on the side, you'll be taking a BMS and just checking its parameters if everything is okay. There, in general, there are about 35 parameters. You attach to this machine, and it would just be like, okay, everything is okay, and then you're okay. You feel okay. Now it's ready to be used in a pack. So you'll be connecting it to the pack, and then the soft pack itself will be put in a battery aging machine, where again, the pack will be charged to 100 and then discharged to 0, to see if everything, all the cells are working together, and the capacity, the battery pack is giving the capacity that we think about, that we expect and all that. And again, it will be charged to a level where the customer is demanding. Most of the customers ask minimum 50% SOC state of charge. And then on the top, you can see how the battery pack is arranged, the BMS is attached, and then you can see the cell holders, the nickel tab, and all that. And then basically most of the time is put in a metal case. Yeah, we'll go to the next slide. Let's talk a little bit about battery recycling. So battery recycling, like I was saying, it's a fast moving industry right now. So many companies are eyeing, but they are trying to, they're not really understanding the basics of it, because it is actually technical. Recycling process is technical for the simple reason that you can't just take cells and just put it for recycling. You're supposed to test the cells. So you can see the value chain over here. So if you see, let's talk about the first process. You take the raw materials and you give it to a manufacturer, and they make some cells, and it is being used in an application like, say, here for cell phones. And then it comes to a collection center when the battery is not able to hold so much of energy. Then it comes to the collection center, and then it is tested. The cells are tested. They are charged and discharged, and the capacity is checked. The IR is checked. The OCV is checked, and based on acceptable value, then it's decided if it goes for recycling or reuse, or we call it as a second life battery. So you can see from reuse, refurbish, again it goes for the sale. So if you are able to repurpose this cell, then repurpose is something many companies are not able to understand, because they don't really understand cells. They're all battery pack companies who are mechanically integrating the battery pack. So someone who has like me, who has worked on cells, so we are able to tell. So what is the right condition for the cell? Like sometimes the cell look fine, but looking at the data, the graphs, I can tell if the cells are not going to last very long, and it's okay to recycle. And if you are repurposing the wrong kind of cell, then again there could be generate formation, and it could catch fire, especially NMC and all that. And if you're confident the cell is useless, it cannot be repurposed, then you will be sending it to a recycling company, which would again dismantle and all that, and send the raw materials to raw material company, and again the value changes goes on. So let's go to the next slide. So this is something McKinsey and company, they made the complete value chain. They're discussing about what I talked about. So a battery pack is sent to an application, and then once it comes back from application, it is tested for if it's good or not, and if it's good, it goes for reuse, and if it's not good, it goes for recycling. And recycling again removes all the metals and all that, and then sends it to the raw material, and it is the same value chain which is talked about here. Let's go to the next slide. So when I said repurpose, so when the batteries are good, but the challenge is batteries. A good battery does not mean that it can be used anywhere and everywhere. So battery pack which has come back from EVs, so they cannot be used for fast charging and high discharge applications such as EV. So the second place that where it can actually go is for energy storage purpose. So this I remember during my college time, this car was very popular. Now it's phased out. So it's a Chevrolet Volt. So this is something General Motors made a display to popularize this, and this was I think sometime in 2013. Yeah. So batteries are removed and then the module at module level. So generally in cars you see modules. It will not be a single battery pack altogether. So each module is tested, and the good modules are put in a ESS pack, and then again it's attached to the grid, where it will be slowly charged from the grid and then sent back to the grid when there's high demand and no supply. Yeah. So we can go to the next slide. So let's talk about the final topic, which is the battery management system. So next slide. Yeah. So battery management system is a component which goes inside the battery pack. So a battery pack has many components inside, like such as cell holder, nickel tab, and then there are other mechanical things like epoxy sheet, EVA foam, and all that, and then the cables, connectors, preferably Anderson connectors, and then the final thing is that is a BMS, battery management system. The battery management system manages the battery pack by protecting the battery. So how does it protect? It makes sure that the battery is operating in its safe operating zone. So what is a safe operating zone? So whenever you make a battery pack, say 48-volt battery pack, so we see that the upper voltage cutoff and the lower cutoff voltage and so many things. So this is something that can be tuned in a BMS, and then a BMS will do as you say, like you want to cut off the battery and all. So the second question is, why do we cut off the battery pack voltage? Why can't we charge it furthermore? Especially in NMC cells, overcharging is a big problem. So if there's no BMS and if you're just charging the cell you cross the limit, and then it's going to catch fire, because you are going against the law of electrochemistry. There can only be certain amount of energy that can be stored inside, and you're just trying to pump in more, and then internally there is a mechanical instability, electrochemical instability, and the cell just catches fire. So a BMS makes sure that the charger uh, is cutting off at the right voltage whenever the battery is completely charged, and then at the same time BMS also makes sure that not too much of current is drawn. So you'll have to use obviously the right kind of BMS for the application. Suppose if you see two-wheelers, they use 40 amps or 50 amps BMS, so it will make sure that continuous current is being given at 40 amps or 50 amps, and it's not being. Sometimes there is a controller failure, and then the motor just demands, and the motor becomes inefficient, and also high amps is just demanded. So if there's a BMS will make sure that no, it will not give you that kind of current, because you're abusing the battery by discharging at higher current rates. So all the predefined things are set in this BMS, and another important thing that it takes care is the temperature. If the temperature generally 65 degrees is what the cutoff is, and recovery 60s, which means if the battery pack is reaching 65 degrees, the battery will just cut off. It will not give any more energy, and then again it will recover at 60 degrees and then start giving. So don't be surprised sometimes if you're driving the vehicle too fast, or you are overloading the vehicle, or you're going uphill and the vehicle just stops. It's okay, it happens in petrol vehicles as well, when the vehicle has heated up. So just wait for a few minutes and the battery pack will come down, the temperature will lower, will go to a lower state, and then the battery will start working fine. So you don't need to panic, and this is something I tell everywhere wherever I go. And then the other important aspect is the lower voltage. You're not supposed to discharge the battery as low as you want. There's a certain parameter set, because after certain voltage there's not any energy that you're going to achieve. Simply the battery would just create a again a mechanical instability, and and that would actually create cell swelling in cell phones. You might have seen some people, the battery is just swelling. So the reason for battery swelling is very simple. You're always discharging your phone to zero, and then and then there's discharging. So generally, I recommend people to use the battery between 15 to 95%. That is the right thing. And one might ask, why don't I use after 95 when I can charge 5 more percent? After 95, the voltage has attended, and it goes from CC to CV mode, where it's a constant voltage mode, the charger, and then it's just heat generation, because the battery is full and you're trying to pump in the last of the energy, and the battery just heated up. And then heat is also a major enemy of the battery. If battery is experiencing heat continuously many times, the battery life is going to go bad. So don't charge fully, don't discharge fully. This is one thing I always tell people. So BMS, if you set all that in BMS, it's going to take care of. Yeah. And then there are two types of BMS. One is hardware BMS, which does all the functions that I just talked about. And then there's a smart BMS, which does all of this. And then there's additional functions, such as, it can record data, store data in a memory card. Obviously, you have to put a memory card inside, and then transmit data. You need to have the, generally in electric vehicles, we use CAN 2.0. And industrially they use RS485 and all that. And obviously you can connect a Bluetooth anytime. You can see the data in your cell phone and all that. So for that's a smart platform where, it's a little bit complicated thing and it's a little bit expensive system, but it is becoming a new standard in the market. So many battery packers are looking at this. Yeah, so we can go to the next slide. So these are all the functions of BMS I just talked about. The lower cutoff voltage, upper cutoff voltage, charging, control the current of the during charging, control the current during discharge, temperature control of the pack and the cells, state of charge. Can now based on the voltage of the pack, you can actually know the state of charge SOC. Say like in our cell phone where we see, okay, 86% of the battery is left. So that is known by knowing the exact voltage of the battery. So there's a small SOC meter which you can always attach. So BMS. So it is attached to the BMS and it can be displayed. And then there is depth of discharge. Depth of discharge is the amount of energy, the percentage of energy that you're discharging from the battery, from a full charge battery. Suppose you're discharging from 100 to 40%. So that means you're discharging 60% depth of discharge. So this is something which it can record and it can enforce as well. If you're setting the voltage in a way that the upper cutoff is so and so, lower cutoff is so and so, it can enforce that kind of depth of discharge that you intend to have. And then there is SOH, which is a state of health. So if someone has an iPhone, they can quickly check up, go to the battery section and see that there's a battery health. So there you will see, say 86% or something, 88%. It means your battery's health is 88%. So a new battery has 100% health, and with aging, the battery retention capacity comes down. So generally in portable electronics, it's recommended to change the batteries at 80%. In EVs, it is 70%. So in iPhone, you would get an alert. In iPhone, you would get an alert as soon as the battery health reaches 80%. It would say, it is ideal. It is recommended that you change your battery. So, and that is one. And SOP, state of power, is this is generally in ESS, energy storage applications, where it would tell you the amount of time the battery will be giving you the energy for on the existing load. So this is very common in UPS and all that, home UPS. So you're operating, say, 3 fans and 2 lights, and it would say, okay, 5 hours of SOP. So that is the amount of hours of energy that you can expect at this existing power of discharge. And then it can additionally store things like energy delivered since last charge, IR of a cell to know the open circuit voltage, number of charge discharge cycles, total energy delivered since first use, and finally total operating time since first use. All these things can be stored in a smart BMS, the last few options. And the first few options are common in both the smart and hardware BMS. So let's quickly move to the next slide. Yeah. So useful parameters in BMS. So this is the last slide actually. So if you are designing a battery pack, you can always get in touch with me. But I thought, okay, you can have the basic parameters. So first thing is, if you discharge, if you see the discharge graph of an NMC cell, there's not much energy left. Like I was saying, you can discharge to 2.5 volts as well, but you're not going to get anything. So simply you're abusing the battery. Simply you're making the batteries go swelling and all that. So after 3 volts, below 3 volts, there's not much energy left. So generally, I recommend that you don't discharge the battery below 3 volts. And if you are using, suppose, say EV, EVs generally, if you're using a good controller, or if suppose you're using a 14S battery, 48 volt battery scooter generally cuts off at 42 volts. So it does the right kind of thing, where 3 volts per cell, that's the thing. So you have to, whenever you're building scooter application, or whenever you're supplying a battery to an application, you need to study the product as well, not just make a battery and just give it. You need to understand what kind of charger they're using. Is it a CCCV charger and all that? Because all those functionalities matter for the BMS, because BMS is the front end communication part of the battery. So that is one thing that you should not discharge the NMC cell below 3 volts. And so you can use a BMS with 2.9 volt, and with tolerance we cut off at 3 volts. Or you can and obviously parallelly you will have to look for a controller which cuts off at 3 volts as well for the application, because controller voltage is on the higher side, and then the BMS voltage is on the lower side. Whenever if you look at application, controller is the first thing which cuts off, and then the BMS. If controller fails, then BMS will come into action. And similarly, there is no energy left in a LFP cell below 2.7 volts. So it's recommended that you do a lower cutoff voltage of 2.7 volt for LFP cells, and avoid charging the cells to completely full charging voltage, which is 3.6 to 3.65 in LFP, 4.2 to 4.25 in NMC. And like I said, cut it off at 95%. That's a good SOC. Don't do anything more than that, because you're simply heating the cells and reducing the battery life. Yeah, and OEM should use controllers, that cut off the voltage before, like I said, just now I said, the controller should have a cutoff function. The voltage should be slightly higher than the BMS cutoff. So that is also something you need to communicate. Suppose you're a battery pack company or you're planning to set up, you need to communicate with your buyers. What kind of vehicle is that and all that. In fact, I always tell people, give them a sample and then go record the data, what kind of amps it is pulling, because sometimes there's not much communication, and they might be testing a battery, they might be procuring a same kind of battery for various applications. So if the ideal battery is something where you use the right kind of C rating of the cells and the right kind of BMS where the continuous current and all that is matching to the application. So I highly recommend people that you work with the OEMs closely, give a battery sample and send the engineer, and then record the amps that during the operation, the amount of amps that is discharging and all. And final note is, if, like I said, don't go all the way to 100%, cut it off at 95. And then if you are actually cutting off instead of 4.2 to 4.1, obviously you will not get 100% of SOC, you will get a lower SOC, but the cycle life almost doubles. You will get a cycle life of more than 60%. And that is something these days most of the OEMs and all are just understanding. I have met few of them, I have told them as well, and some of them know this the fact as well. So you're not supposed to charge the battery all the way. If you look at data sheets, it says 4.2 upper and lower is 2.75. I tell people don't touch the limits either side of the battery. And the final thing I want to say is batteries are classified as dangerous goods, so please handle it with the right signs. It's not just please handle it carefully, use the right signs to handle it, or else you're seeing a lot of fires coming in the market, and you will see some more in the future. It's bound to happen if you don't follow the right signs. So people be careful with battery. It's something that can be avoidable if you're using the right signs. So yes, that will be the end of
Okay, thank you so much for your great presentation, Mr. Rahul. So
Yeah.
I believe you had touched upon all the questions that were asked previously about the recycling of lithium ions, about the overcharging, about the battery capacity. So yes, I can give you one question which was asked by Mr. Rajpin saying, can a two-wheeler EV battery be charged overnight? And I think this question is also connected with the other question, which I feel is like the charging of battery more than 100%. So I think you can quickly summarize and say about that
Correct,
question.
yeah. So basically, you're talking about overnight charging. See, you can
Yes.
always, even if the charging takes 2 hours, after that the charger will have a cutoff, and then it's not going to charge. So the
Okay.
advantage of overnight charging is basically um, this is something for the car where we don't have that kind of load. So Tata Nexon has a 30 point some kWh battery. So our home load, if you're trying to do a fast charge of 2 hours, we don't have a connected load at our home for 15 kW to give that kind of thing. So overnight charging is something for big batteries, but yes, slow for two-wheeler as well. Two-wheeler generally you get a 6 amp charger, and two-wheelers have anywhere from 26 Ah to all the way to 40 Ah. So technically 40 Ah battery using 6 amps would take 7 hours. So that is technically overnight, and suppose you leave it at 8 in the night and then you want to remove it 8 in the morning, it's okay. 7 hours will be charged, and next 5 hours the charger will have a cutoff. The BMS will have a cutoff.
Okay.
So you can leave it like that. So using a slow charger has its own advantage.
Okay.
So the batteries will not heat up, and batteries do heat up a lot while charging, especially doing fast charging. So that is one thing. And what was the second question was battery charging till 100% or more. See, till 100 is not a problem. More than that, see, every battery pack has a BMS inside. Hyundai Kona. There was a Hyundai Kona which where the batteries caught fire in Canada. So there the BMS failed. So if the BMS fails, obviously overcharging is going to happen because chargers will not have any cutoff function. And there will be a communication generally, but the communication is much more stricter in the DC fast charging. But in slow charge at home, the electronics are very simple. They are budget friendly kind of thing. So there, if any electronic failure happens, then yes, batteries can catch fire.
Okay.
It is a possibility, but it is a very rare possibility. I would say maybe 1 in 100,000 kind of thing. Which is, I think, it happens in IC also. There is a leakage and all that. So safety wise, yes, this is being highlighted in a more way. But I can tell you, it has never killed anyone till date, and the numbers are similar to petrol, diesel power.
Well, I think that question has arisen by the videos that has been circulated, and I think the mobile phone.
Yeah, like I said, yeah. See, that is the right science is the problem.
Yeah.
So see, if you are discharging your batteries too much, the batteries are going to swell, and then a swelling battery, if you're just using it, you're supposed to change the battery at that time. Sometimes the swelling is not even known. So that's why I tell people use the right signs. The right signs is, is charge whenever the batteries drop to 15% and don't charge above 95. It's okay if it's sometimes the charging is so fast, we don't even know when it hits 100. It's okay, the charger will take care. But one thing I always recommend is don't let your batteries go below 15%. It is going to swell your cell.
Okay.
Yeah. And all these things which are happening in the Okinawa, Pure EV and all that, what you're seeing in the market, all that is an internal short circuit issue. That is not during something charging. That is, you can see the vehicle is clearly kept on a road. It's not during the charging condition like the Hyundai Kona. So internal short circuit happens when the cells, this is a popular thing whenever you're using cells which are not so good quality. It's a very common thing in India. If you're buying a cheap electric vehicle, obviously their budget is also low. They try to procure low quality cells and all that. And the low quality cells, there will be some mismatch and all that during operation itself. And first of all, it will start with, you can know the indication when the batteries are delivering low range. The range just drops within a matter of months. So in 6 months, you will see the range would have dropped by 15%, which is not a good thing. And then you will see the batteries, and slowly, because one of the cell is peeling, and one of the cell will have an internal cell short circuit, and that will, the whole pack will catch fire. It's just that one cell which is, creating that issue. And why that one cell is coming inside is you're buying cheap cells. So in that lot, some of the cells are good, some of them are not good and all that. For cost reasons, it's happening. Yeah. But if you're buying branded vehicles and all that, they who are using LG cells and all that, so that possibility is almost next to zero.
Okay.
Yeah. So now these companies are working towards, procuring better grade cells because they have burned their fingers and all that. So it's improving now. Yes.
Very good. So I believe indeed, audience, please take a note of all these points which Mr. Rahul has said. It is something that actually is not only relevant to the batteries, but also, about your life. So safety and also your precautions and all the, points and tips that Mr. Rahul has said. Please take a note of that. And
I'll share my email address in the chat box. So any questions, people can just email me. Okay.
Yes, that would be great. So
Okay.
thank you so much, Mr. Rahul, for joining. I think we have exceeded our timeline, but no worries. Knowledge is always important. So thank you for joining us, Mr. Rahul. I hope you have a wonderful evening. Thank you.
Thank you.